Let us continue mixed potential theory and let us see whether we can explain some of the corrosion examples. Last lecture we have seen the effect of galvanization on steel. Let us say you have zinc rod and iron rod, both are immersed separately in two beakers containing the similar HCl acid of the similar quality. Then we have seen that the zinc corrosion rate is less than the iron corrosion rate if they are immersed separately in HCl solution. But we have seen that if iron and zinc are galvanically coupled and immersed in HCl, then the situation is reversed. Now, the situation would be here, the iron corrosion rate would be greatly reduced, and whereas the zinc corrosion rate will enhance. We have tried to explain with reference to mixed potential theory. Now, let us take few more examples. Let us see another one example is, let us say that if that one was, let me take one example. That example, if we have HCl acid which is not pure and which is all still deaerated HCl acid, and in that HCl acid we have impurity, and that impurity is nothing but ferric ion, Fe plus 3 ion. Now, you have two beakers, and one beaker you have HCl, deaerated HCl, which is pure, it does not contain any impurity, but in this case you have HCl plus Fe plus 3. Now, if you immerse one zinc block, here also you immerse zinc block of the same quality, then you will see the corrosion rate in this case will be much more than that of zinc in HCl. So, if you consider the corrosion rate in this case would be greater than corrosion rate in this case. So, sorry, this is just reverse. Yes, it is fine. So, corrosion rate in this case would be much more than the corrosion rate of zinc in pure HCl. So, let us find out what should be the reason. Now, again let us plot two diagram. In one case, let me first try with, this is potential, which is nothing but Evans diagram, and this is log I, where small I means the current density. Now, let me see where we have E0 for zinc plus zinc, and it should be, if you are taking standard condition, then it would be 0.76 minus volt. Now, in this case the cathodic reaction would be hydrogen evolution reaction. So, hydrogen evolution reaction corresponding potential E0 of H plus H2. So, now this is my I0 on surface, this is my point, and I0 for hydrogen on zinc would be around this. So, now we would like to see where is my equilibrium point. Now, equilibrium point where the charge transfer rate would be same, it means that the rate at which electrons will get consumed would be equal to the rate at which electron will be generated. So, now you have seen that you have this situation. Now, this is the point which is nothing but I core for zinc, and here I C would be equal to IA. That means the cathodic current density would be equal to anodic current density, and this would be equal to I core. And the reaction what is happening here is H plus E H, and in this case it is zinc going to zinc plus 2E. Now at this point the rate at which electrons are getting consumed would be equal to the rate at which electrons are getting generated because of this anodic reaction. Now this is the case what is happening in this case. In this case, in the case of pure HCl, where you do not have any other cathodic reaction, only one cathodic reaction, which is hydrogen evolution reaction. You can put it like this: hydrogen evolution reaction, you put 2 here. So now you have the equilibrium point at this point, and the corrosion potential, this would be my corrosion potential, which is nothing but E core. Now let us see what happens here. Now in this case we have H plus ion. Now H plus ion can get reduced and it will go to H or H2 gas, 2 H plus ion. When this 2 H plus ions will be reduced, it will form 1 mole of H2 gas. Now there is one more species available in the solution which also leads to a cathodic reaction. That cathodic reaction is nothing but Fe plus 3 plus E going to Fe plus 2. This is also a cathodic reaction. Now this reaction, the potential is nothing but E0. Fe is around plus 2 plus 3 going to plus 2, it is around 0.77 most probably. This is volt with respect to the standard hydrogen electrode. Now this is plus, and here E0 is basically 0 volt with respect to standard hydrogen electrode. Now since we have one more cathodic reaction, so it also should happen in the same system, and let us say this is my 0.77 volt, and from that point we have to see that how this reaction is happening. So let us say this is my point, which is I0 of Fe plus 3, Fe plus 2, and this I0 for this reaction is happening on top of zinc surface. So I have to mention zinc in the bracket, I have to include zinc. So that means this reaction, the exchange current density of this reaction happening on zinc surface. Now let me see the activation polarization for this reaction. So this line gives you the cathodic activation polarization for this cathodic reaction. So I write this equation as Fe plus 3 plus E going to Fe plus 2. Now the line is coming, if this is not happening, so this line will go and this will cut at this point. So this is the, if this hydrogen evolution reaction is not happening, so in that situation this should be the point where I would get the equilibrium between the rate at which electron is getting consumed and the rate at which electron is getting generated. So this would be the new point. But now when it reaches to this level of potential, which is 0 potential, let us say this is 0 potential, which is standard hydrogen electrode potential. Now at this point when it reaches, now it experiences one more cathodic reaction. So that cathodic reaction is nothing but the hydrogen evolution reaction. So we have to, as we have seen in case of galvanization of zinc on iron surface, Same thing would happen here. So we have to add up all the cathodic currents. Now if we add up the cathodic current, so you just add it up and it will be along this line. It will be along this line, because now this is nothing but I for H plus H, the cathodic current for H plus going to H, that cathodic reaction, and this is for I of Fe plus 3 going to Fe plus 2. And what is the red line? The red line is basically nothing but IC, which is total. Let me mention total. The total cathodic current density would be equal to I of H plus H plus I Fe plus 3 Fe. And this is in the straight line because it is in log I scale. Now what would be my point where I would see the rate at which the evolution or the generation of electron would be equal to the consumption of electron. Now if you say that at this, if you extend this line, if you extend, this line is cutting at this point, So what would be my, this is my new IA for zinc going to zinc plus 2 plus 2E. This is my anodic current density along this line for zinc corrosion. And what would be my total cathodic current? Total cathodic current would be this. So at this point we see the rate at which electrons are produced from this anodic reaction would be equal to IC total, because IC total means electrons, part of this electrons which are getting generated because of this anodic reaction will be consumed by hydrogen reduction, hydrogen plus reduction, and part of those electrons will be consumed by for the Fe plus 3 reduction to Fe plus plus, Fe plus 2. So now we see that this should be my new corrosion current density, which will be equal to I core. So this is my I core, and it is in log scale. So if ferric ion is not there, so my current density, corrosion current density is this much. If ferric ion is there, my corrosion current density is this much, and since this is in log scale, so it would be of the order of 10, some orders of 10. So let us say if this value is 10 to the power 2, this value could be 10 to the power 5. So I am just giving you the rough estimation. So now the corrosion rate has increased to a great extent because of this Fe plus 3 presence, and the phenomena is happening like that. Now there is another interesting phenomena that is going on parallelly. What is that? Let us say with the yellow line, let me put what is my corrosion potential, E potential, corrosion potential E core. So E core would be the corresponding point. This is the yellow line tells you the E core. Now what would be my IA here? IA is this one. So let me put some points. Let us say this is my A, this point is B, and this point is C, where this line, parallel line along E core cuts this hydrogen reaction and Fe plus 3 going to Fe2 reaction. So that means this is basically nothing but I core or the dissolution rate, anodic reaction rate, and which point corresponds to I core of hydrogen. So I can write it as I core I H plus of H plus I Fe plus 3 Fe plus 2. This point is nothing but A point. And what is this point, which corresponds to the current density along the C core, which is nothing but the C. So this is C point, and which one is B point? B point is this. So this is my B point. The current density corresponds to B point, which is nothing but the current density of that iron reduction. C point corresponds to the current density of hydrogen ion reduction, and A point corresponds to the zinc dissolution rate or anodic current density, of which is nothing but this point, or it is nothing but the I core. Now interestingly, if you see, if Fe plus 3 is not there, what is my evolution, hydrogen evolution rate, if this one is not present? So that means before drawing this curve, this top curve, I have drawn this one first. So if Fe plus 3 is not there, which one is my current density, equilibrium current density, which is equal to the anodic current density, equilibrium current density for cathodic reaction? This is my cathodic reaction rate if Fe plus 3 is not there in the solution. So now you see, without having Fe plus 3, I have this much of hydrogen evolution rate. But if I have Fe plus 3 in the solution, my hydrogen evolution rate is nothing but this one. So if this is, let me say, D point. Now if you compare the current density corresponds to D point as well as C point, then I see that I H plus H is at C is less than current density of H plus H at D point. So that means if you don't have this, my hydrogen evolution rate on zinc surface would be much larger than the case where Fe plus 3 ion is present. So if you have Fe plus 3 ion in the HCl solution, my hydrogen evolution rate will be reduced. Now what is happening? Because of polarization, if you consider the polarization effect, so let us say I am considering the polarization. Polarization means, let us say I am considering the cathodic polarization. Cathodic polarization means if this is my polarization and this is my 0, which is basically corresponds to the exchange current density. Now that point, if you start the polarization, cathodic polarization, it will move along this, and this is nothing but log I. And if you have more and more polarization, which is nothing but the more and more value of over voltage, you see the rate of the cathodic reaction is increasing. Let us say I am here, which is my, this much is my polarization N1. Let us say I am here, so this much would be my polarization N2, neta 2, and this is, I am here, which is the polarization is this much, which is neta 3. And you see, as neta 1 less greater than neta 2 greater than neta 3, so that means as you are increasing polarization, you are also increasing the rate at which cathodic reaction is happening. So I1 IC1 would be less than IC2 would be less than IC3. IC is nothing but the cathodic current density. So that means as you go along the polarization line, or as you increase the polarization, degree of polarization, you are going to increase the rate at which the cathodic reaction would happen. But here you see, without this presence, I can reach to this level of polarization. I can reach to this level of polarization. This level of polarization. But in case of hydrogen, but if you have this, then I can only reach up to this. That means instead of having polarization up to this, or instead of having this much polarization, I am getting a much smaller polarization or much smaller over voltage. That suggests that this is acting as a depolarizer for hydrogen evolution reaction. So, iron ferric ion is acting as depolarizer for hydrogen evolution reaction. And Fe3 plus is also called hydrogen depolarizer. Hydrogen depolarizer. So, now we have two distinct effects. One is, if you have impurity like ferric ion, I would increase the corrosion rate of zinc will be increased in HCl solution. At the same time, you will see the hydrogen evolution rate on the zinc surface will be reduced. So, if you have this and this, you will see the bubbling would be more here, you will see the bubbling would be less, because here the hydrogen evolution reaction rate is this much, and here the hydrogen evolution reaction rate is this much. So, this is one example. Now, let us also find out some more example. Let us say we have considered the galvanizing effect of zinc on iron surface. Zinc corrodes, and in a way it protects iron, but it does not mean that iron corrosion is stopped. It means that iron corrosion rate has reduced because of the zinc corrosion, and more zinc corrosion. So, let us have second example. Let us have second example. The second example would be, let us see what happens. We have seen if you combine iron and zinc and put it in HCl solution, you will see that I rate at which the I core would be less than of iron would be less than I core zinc, and this is nothing but the effect of galvanization. That is why galvanization is done with zinc on iron surface. But if we combine platinum with zinc, in one case, this is case 1, and if we combine gold with zinc, this is case 2. Now, what would happen? Let us see what happens here. This also can be explained quite naturally from mixed potential theory or from this graph. The same kind of graph, we will draw a different curve now. Now, in this case, let us say I will have the cathodic reaction. Let us consider only one single cathodic reaction, which is nothing but H plus E going to H2 gas. So, hydrogen reduction reaction, let us consider that only. We are not considering any other cathodic reaction. Now, when you have these two couples, let me first consider one important aspect. We have seen that the exchange current density has a great effect on the actual corrosion phenomena, that we have seen in case of galvanization effect in this case. Similar sort of effect would come here. Let us find out. You can see that if you consider log of current density I, log of current density, and if you like to plot the exchange current density on this scale, now this is my potential, let us say this is my 0 volt for hydrogen evolution reaction, and the hydrogen, let us say these are two couple. Now you have platinum surface, you have zinc surface, and hydrogen is going to be evolved on this surface as well as on this surface. So what would be my, that means on this surface this reaction is happening, and on this surface also this reaction is happening. Let me see what would be the value of I0 of this I0 for this reaction, or exchange current density of this reaction. So on the zinc surface this value is about 10 to the power minus 11. So it is around, just a minute, let me have a look at it. Okay, it is around 10 to the power minus 11 ampere centimeter square. This is I0 of hydrogen on zinc surface. Now let me also find out what should be the I0 on gold surface for the same reaction. Gold surface would be around around here. So which would be around 10 to the power which would be around, let me just find out the value. This is 10 to the power minus 2 minus 3, it would be around 10 to the power I0 of H plus H2 on gold would be equal to around 10 to the power minus 6, around 10 to the minus 6 ampere per centimeter square. But it will lie on the same line along the 0 volt. This is 0 volt, this is potential, and this is log I. Now the similar way, the value of this reaction, value of exchange current density for this reaction on platinum surface will be around, this is I0 H plus half H2 on platinum is around 10 to the power minus 2 ampere per centimeter square. So this is the sort of data we have. Now this data will decide what would be the actual corrosion rate and what would be the effect of this noble metal attachment to zinc. Now in this case again let me draw E versus log I. And this is E, and let us say this is my E0 of zinc, and this is, let us say this is my I0 of zinc plus zinc on zinc surface. And let us also see the anodic polarization line. The anodic polarization line, it gives you zinc plus 2E. Now if there is no coupling, then we have this situation. Let us say this is my 0 volt, which is nothing but the hydrogen evolution reaction standard reduction potential. So that value is around this. So I have to see the cathodic polarization also. So this is nothing but H plus E going to H2 gas. And this is my point where this is nothing but I core, which is nothing but IC, which is nothing but H plus H2 minus, I would put a minus here because just to indicate that IC is flowing opposite direction than that IA. This is nothing but IA, this is IC. Now this is before coupling with the noble metal with platinum or gold. Let us see, if I club it with gold, then this reaction is also taking place because this is I0 of H plus half H2 on zinc surface. Now I have to consider this value, the relative value, it's on the right side. So let me see this. This is my point, which is nothing but I0 on gold surface H plus half H2. So we have this also as well as this. So this is my hydrogen reduction line for those hydrogen reaction which are happening only on the gold surface. So now you have two cathodic currents. One is cathodic current for the hydrogen evolution on zinc surface and cathodic current density on gold surface for the same hydrogen evolution reaction. So if there are two cathodic reactions which are parallelly going on, so we have to add these two things, two current densities, to find out the total cathodic reaction rate or total reduction rate. So the total reduction rate again will be following. You have to add these two currents and then it will follow this line, this red line. And then where do you think that the total reduction rate would be equal to total oxidation rate, or the total anodic reaction, total current density for anodic reaction would be equal to total current density for cathodic reaction. The point would be, this one would be my new point, this one would be my new point, where you see the current density, anodic current density, the anodic current density IA, which is nothing but zinc plus going to zinc plus 2E would be equal to IC total with a negative sign, because I am just putting negative sign. Even if you take the mod value, then this negative value will go. This negative value is nothing but the direction, but magnitude wise both are same, and this would be equal to two contributions. One contribution would come because we have to see where is my E core. E core would be my this point. So this is my E core and this is my IC for hydrogen evolution on zinc surface, and this is my point which tells you the I0 IC for hydrogen evolution on gold surface. Fine. So this plus this equal to this. So this would be equal to IC of this. So let me put the points. This is A point, this is B point, and this is C point. So would be equal to A plus B plus C, or you can write it as IC on zinc plus IC on gold, and there would be negative sign because we are taking direction also into consideration. So then now you see, if you have this noble metal coupling, the zinc corrosion rate increases quite largely. So here you see in the log scale value, the zinc corrosion rate with gold coupling is this one, and zinc corrosion rate without gold coupling is this one, and this is in log scale. So you have a many times increase in the corrosion rate if you couple this zinc with the gold. So this is one example why with the noble metal addition to zinc, it increases the corrosion rate of zinc. Generally we have that notion that if we add gold, pure noble metal into an active metal, the corrosion rate improves, corrosion resistance improves, but it actually is reverse. If you add gold into zinc, corrosion rate of zinc increases, and this is the beauty of mixed potential theory, and this phenomena can easily be explained from this. So we see the effect of noble metal addition in an active metal like zinc, and we see the zinc corrosion rate increases to a great extent. Now similarly, if we have this couple, and in this couple and in this couple, the main difference is same hydrogen evolution reaction is happening, but here the exchange current density on gold surface for this reaction is less than the exchange current density of this reaction on platinum surface. So what would be that effect? So in that case, I am not removing the gold part. This couple is a separate couple. So I am just putting this what happens with respect to platinum on the same curve, but it should not be mixed up like that gold and platinum both are added to zinc. So this is a separate situation, and the case of platinum will be another situation, as a different situation. So that case, let us find out what happens in case of platinum. Now let me put the I0 on platinum surface. So this is my I0 of H plus H2 on platinum surface. Now that means you have hydrogen evolution and reaction, and the same way you can have polarization reaction of hydrogen evolution, polarization effect for this reaction on platinum surface. So this is my polarization of hydrogen evolution reaction on platinum surface. Now you have two reaction, one is happening, you have basically same reaction happening on two surfaces. This is one situation where you have hydrogen evolution reaction on the zinc surface when it is coupled together, and this is my hydrogen evolution reaction on platinum surface. So you have two cathodic currents coming from same reaction. So this is one cathodic current and this is another cathodic current. So what would be my total cathodic current? Total cathodic current would be this plus this. So I have to indicate that total cathodic current on the same plot, and that would be, you have to just add it, that would be this one. Now you see there is one small difference. You see the gap between these two lines when you are considering in the case of gold is more than the gap between these two lines, which is the total and platinum, total cathodic current and the current density corresponding to the cathodic reaction on platinum surface. Why it should be? Because here we are adding in the log scale. So if you are adding in log scale, so this would be much closer to this line. So because since it is on the right, it is on the increasing side. So now what would be my new point where I have the total rate of cathodic reaction would be equal to the total rate of anodic reaction. Here only one anodic reaction is taking place. So, let me extend this line, let me extend this anodic line, and let us see where it curves to the total cathodic reaction rate line, and total cathodic reaction rate line is nothing but two cathodic current densities corresponding to the single reaction, which is nothing but the hydrogen evolution reaction. So, this is my new point and this is nothing but I core, and let me put bracket platinum, because this I core of zinc, when zinc is coupled with platinum. Now, you see my I core on platinum, in the case of platinum coupling, is much higher than the case where you have coupling with gold. So, you see main point is this increase in corrosion rate of zinc because of galvanic coupling with noble metal is happening because of this situation, because of increased exchange current density for hydrogen evolution reaction. So, you see the importance of exchange current density. It actually tells you the actual kinetics of the reaction, corrosion reaction. So, this is my, again with respect to, if you couple zinc with platinum, its corrosion rate of zinc will again further increase, to a great extent. So, this is the effect of noble metal coupling, and on the way the effect of exchange current density on the corrosion rate of active metal. So, this is another example. So, let me consider one more example. This is an interesting issue. This is area effect. What would be my area effect? Now, let me first tell you the actual, what happens in actual situation. If you have iron plates, two iron plates, and if you join these two iron plates with a copper rivet, this is situation 1, this is copper rivet and this is iron plate, and another situation is you have two copper plates, this is copper, made of copper, and you have iron rivet. And these two things, if you dip it in seawater, you will see the situation, the actual observation would be after some months, this joint will be loose, very loose, but this joint still it maintains some sort of strength. This joint will be strong, but this one would be really loose. So, what is actually happening there? So, the main reason is, here you have, here the cathodic reaction is nothing but this is my cathodic reaction, which is happening in both the situation, and cathodic reaction would be, anodic reaction would be Fe going to Fe plus 2E. Now, in the galvanic series, copper is on top of iron, So, galvanic series, it does not give you any potential value, it gives you only the relative position with respect to solution. Now, if copper is placed above iron in the galvanic series, then copper is noble and iron is active. In seawater, copper is placed on top of iron. It means that the cathodic reaction happens on the noble metal surface, and anodic reaction would be the reaction of that metal which is staying below that noble metal. So, in this situation, copper is noble. So, this reaction would happen on copper surface, and this is active. So, anodic reaction would be nothing but the iron dissolution. This is my anodic reaction, and it is happening on iron, and then iron is nothing but the active site, and copper is a noble site, and this noble reaction is happening, or the cathodic reaction is happening. If cathodic reaction happens on a particular metal surface, so you are not getting the electron discharge reaction. If electron discharge reaction is not happening, it means that it is a protection. Cathodic reaction happens on some surface, that surface is getting protected because of this cathodic reaction, but here you have iron reaction. Now, in this case, so this couple, if you connect it, there would be current flow, there would be some current flow, and if you would like to measure the current density, in this case, iron surface it would be IA, copper surface it would be IC. The current which will flow in the system will be decided by the amount of cathodic and anodic reactions. Here the surface area which is available for this cathodic reaction is very small. So, accordingly the current value would also be small, and accordingly if you consider the value of IA, because that current value, if I value if you consider, and the total amount of cathodic reaction if you consider, this I would be small. So, correspondingly IA, which is nothing but I divided by A of anodic surface. So, here A of anodic surface is huge because you have huge iron surface. So, this is very small, and IA is nothing but the corrosion. So, if IA, which is the current density for anodic reaction, is small, so the corrosion rate of iron would also be small. But here the situation is reverse. Here you have iron rivet. If I, for example, let me complete this. If iron corrosion rate is small, so the rate at which iron will dissolve around this rivet position would be very small. So, gradually it goes away, iron goes away from this rivet region, but the rate at which iron dissolves is small. So, this joint strength can remain for a longer period. But here the situation is different because you have huge copper surface available for this reaction. So, if you have more and more of this reaction because you have a huge cathodic area, so your current would also be very large. If current is very large, the same current is flowing through this iron region, and here the iron region is very small. So, what would be my IA in this case? IA would be very, very large, because IA is nothing but I divided by capital I divided by A and fine. So, you have huge current and a very small anodic area, and consequently the consequence of it would be very, very high current density for anodic reaction. But in this case total current would be less, the anodic area is very large, so IA would be very, very small. So, in this case if IA is very large, so the rate at which this iron rivet goes into the solution is very, very large. So, gradually, since the rate at which iron dissolves from the rivet portion, the rivet will actually go away. There will not be a very small tiny part will remain in this region. So, if rivet is not there, so you do not have strength in the joint. So, this will be loose, but this will still maintain its strength because of this small IA. So, the same thing can we explain from this? We can definitely explain this. Let us find out what could be the possible explanation from this exchange, from this mixed potential theory.